Welcome back everyone, my name is Pedram and this is where we do advanced time series analysis, deep forecasting. Alright, let's do module 7, deep sequence modeling, and we're going to talk about LSTM today. This is the third theory lecture of this module. In part 1, we saw how DNN and RNN architectures are treating your time series data fundamentally differently. And in part 2, we talked about the details of recurrent neural network. So this is the third part that we're going to talk about gated unit cells and the details of LSTM. So part 3, deep sequence modeling, gated cells, LSTM. So in this theory lecture, we will be specifically talking about this concept of gated cells. And let me quickly remind you what do we mean by those cells. So this is what we call them perceptron or neurons or nodes or units in module 6, right? So remember in your simple DNN, let me pull up in your simple DNN, we had some features and then we connected them to the first layer, hidden layer. And inside the hidden layer, we have something called neurons, right? So this, we show it with a circle, and this was your neuron. And we said that inside each neuron, there are two things going on, right? There's a summation and activation. So we showed it something like this. There was a Z and sigma. And at the end of the day, we said that the output of each neuron is something like this. You know, it's we can write something like this. It's an activation applied to a summation term. So we showed these are the weights, WTX plus some bias term, right? So this was what you saw inside a neuron, inside a cell. There was nothing fancy here, two simple mathematical operations, a simple summation, and a nonlinear activation function, right? For RNN, we said, okay, now let's look into these recurrent neurons, right? So the recurrent neurons, we showed them with them square, and inside that square was the exact same thing, right? We had those two operations, right? We had this summation activation. So we had something like this. We have a nonlinear activation. We applied it to our W2X. And then this was the new part. We added this recurrent concept, right? We said that we can add all these recurrent units, we can connect these state vectors to each other using another matrix, right? So we could show it with U, for example, we did something like this. Like U, and then coming from previous state, right, HT minus 1. So the inputs of this was different from DNN, and this was the new part, right? We said we are connecting these hidden states with the weight matrix of U, right? And then imagine we have 4 of them, we were stacking them like this, right? So this was our simple DNN, this was our simple RNN, and then as you can see, these neurons, these cells are not super fancy. They're simple summation operations inside them. Now we're talking about gated cells. So this is another cell. So again, in neural network, it was a circle, something like this. In RNN, it was something like this. And now in gated cells, in LSTM, it's going to be something as fancy as this. So we're going to talk about these concepts of gates, right? So we have, for example, in this picture, we're going to have a bunch of gates. You know, we are going to have 4 gates here, and we're going to explain all the details of what do we mean by them, how they're going to help the network to develop something like long-term memory. Because remember, in RNN, this is where your short-term memory was forming. In LSTM, there's a combination of short-term and long-term. So we're going to talk about all those stuff. So here's the deal with today's video. You know, what you're going to see in the next hour or so is going to be actually a recording from one of my recent classes. And let me tell you, it's one of the best sessions I've ever done. And the energy was high, the students were engaged, and honestly, they loved it. I've been teaching this stuff for a while now, and this iteration, it just clicked. So that's why I really wanted to share it with you guys. And now, full disclosure, since this was a recorded live session in class, the sound quality isn't quite up to the polished standard that you might be used to here on this channel. But I want to apologize for that up front. It's not perfect, and you might notice some background noise or moments where it's not crystal clear. But here's the thing, the content is so worth it, and I've listened back, and overall it's totally listenable. So I think you're gonna still get all the good stuff and the idea, the insight, the vibe, and everything. And as I said before, this turned out to be one of the better sessions that I've ever done when I'm teaching LSTM. So that's why I wanted to share it with you. So the rest of the video is going to be that recorded session from my class.
Okay, so we want to open this recurrent cell. It used to be a simple one. Remember, we had something like this. This was a recurrent neural network. Now we're going to make it super fancy. We're going to introduce the concept of gates and what are each of these gates are going to do. And then now we're adding this notion of short-term, long-term memory, right? So at a very high level, I just want you to just stare at this cell, hey, and look at the inputs and outputs, right? At the end of the day, what are the inputs? We have a bunch of features. So this is your input. And we are taking something from the previous hidden state. So this is also going to be the input. So these are going to be your inputs. And the output, it used to be only what happens in this hidden state. Now we are outputting something else as well. So we are outputting this longer term memory, right? These are the same. This STM, these are the same. These are the same. And right, same. I don't know, for whatever reason they wanted to show it. Okay, one go up, one go down, but honestly, they're basically the same thing. The idea is that here at the bottom we can think of this h of t as your short-term memory. So short-term. This is where the short-term memory is basically forming. And now we are at it. So if I just say I have ht minus 1 xt, and then you're outputting ht, this is nothing fancy. This is going to be your simple RNN. The new thing that we're introducing is this one. We call it carrier state or cell state. So this C stands for carrier state. CT. This is going to be your long-term memory. And I'm going to show you how how beautifully this long-term memory is going to form using LSTM, right? At the very high level, inside this thing, we have 4 gates. The first one is going to be your forget gate. Then you're going to have input and update gate. So there are 4 things, 4 set of weights here, inputs and update. So I can say input gates and update. And then the 4th one is output gate, right? So we're going to see why we need them, what are they doing exactly, and talk a little bit about, at this I'm going to walk you through about the weights and how many set of weights we have and compared with RNN. Sounds good? High level? Again, the difference between RNN and LSTM is that we are adding this notion of carrier state, longer term memory. And we will see how mathematically we're going to do that. All right. So why should we go beyond RNN? RNN can handle all these things. It preserves the order, so this is a good thing. CNN also preserved the order, but it was not as effective as RNN, right? It can handle different input length. This is the only architecture that can handle different input length, right? Sequential models in general. And it shares parameters, right? We said that if we have a bunch of these cells, these are our recurrent cells, recurrent neural network. And then we show something like this, and I have my X. We have WX. We have this. We show it with U. We can show it with WU. And then there's if it is many to many, each cell has an output too, right? So we can show it with YT here. If it is many to one, there's only going to be one of them, right? So we are sharing these weights. So the point is that these weights are shared in the entire network among whatever time sequence you have. So for example, you can have 120 sequence, you can have 20 of them, right? But the shares are weights across all those things, right? So what was the limitation? The limitation was that this RNN does not count for long-term dependencies, right? And that the problem was when we calculated this backpropagation through time, we saw that, okay, what if the sequence that I'm passing to this network has 120 length, right? So it means that you have to calculate those derivatives 120 times. And if you multiply 120 small numbers, it will go to 0. Okay? So that was the problem. So that's why effectively RNN can handle sequence length of 20, 24, 30 at most, and that's it. It's not going to remember anything behind that. What does it mean it's not going to remember? Because if the gradients get 0, then your weights are not going to get updated. So it's going to get stuck there. So that's what we mean that it doesn't recall anything from 30, 40, 50 steps behind. So that's why we need to come up with a new architecture, right? So again, the problem was vanishing gradient problem, and there are some solutions to this, right? So vanishing gradient problem, how can we solve it? And these solutions apply to any kind of architecture, not necessarily RNN, but we will focus on the one that's going to fix that for RNN, right? The vanishing gradient problem is there even for deep neural networks, right? But that problem is exaggerated for RNN because the number of those gradients that you're multiplying is high. It's much more. So what is solution number one? We can use different activation functions, right? So if I know that if I use either sigmoid or this is my sigmoid standard logistic, right? Or tanh, this is tangent. Especially at the very end, and I just want to remind you that, guys, this sigma is the function itself. Sigma prime is the derivative, right? So the gradient is the derivative of something, right? So you have to look at that. So let me actually color code this one. So this is going to be your derivative. Right? I know that sigmoid itself is between 0 and 1, but the derivative it's a lot smaller, especially look at the ends. So if you're passing something to that sigma and you're on the either left side or right side, the odds that that number is small is very high. So I don't know, we have for example, this number is 0.09, right? And just imagine if I multiply this number 10 times, it's going to go to 0, right? So that's the problem. The same story for tanh, right? So this is the gradient for tanh. Again, the same problem. The gradient is pretty much close to 0 at the end. And but however, for the ReLU, look at that. For ReLU, the gradient is equal to 1. So this means that if I have 100 of those sequences multiplied to each other, as long as it's positive, it's 1, 1, 1, 1. It's going to be 1. Okay. And the problem with ReLU is that what if those values that you're passing to the activation function are negative, then your gradient is going to be 0. So it's going to be cut right away. But the ReLU, so the solution to that is say, okay, maybe if that number is negative, maybe use something called leaky ReLU, right? It's not flat. It's not flat anymore. It's going to be a little sloped, and that slope is going to show up here. So this is going to be a small, I don't know, 0.05-ish, for example, whatever it is, right? What I want you to pay attention is that, look at that. If I have ReLU, and if the network is deep enough, and we have lots of layers, we use this ReLU multiple times, the rule of thumb is that if your network is deep enough, your neurons get enough chance to show up in the network, right? So even for those of them who are 0, eventually, when you're doing different randomization, probably you'll get to this positive part, and then multiplication of lots of those positive parts are going to show up eventually in your weights, right? So I'm not super worried about these zeros. The problem with these ones is that we are close to 0 for a very long extended range, and multiplication of them are going to go to 0. So that was one solution, right? And sometimes you have to use sigmoid, right? So this is the last layer, or you want to do something. What if you have to use sigmoid? What else can you do? Another thing that you can do is that, look at that, guys. I have large positive numbers, I don't know, 2.5, and large negative numbers, magnitude-wise, minus 2.5. How about if I can normalize them, right? If I can normalize them and shrink that distribution. So this is another solution, right? So if I shrink this distribution somehow, then it's going to end up with something like this. And maybe it's less exaggerated, right? So this is another solution that we're going to do. You're going to work with sigmoid, but you're going to do something called batch normalization. So normalize the output of each layer and then pass it to the next layer. So that's what we do as one of the other solutions. Another one is weight initialization. So it's simply, this technique is super simple. It's just make sure that your initial weights are not too small, right? So remember, guys, this is neural network, and we said that there's no closed form solution. Your software has to start from somewhere, from some random weights. Those random weights, we just need to make sure that they're not small. Okay? So that's another solution. And another solution is something called gradient clipping, which is the opposite of gradient vanishing. So we want to cut it. So sometimes your gradients are exploding. So this is going to gradient clipping simply is going to limit the magnitude of those gradients from becoming either too small or too large. So if your gradient is, I don't know, a large number, just put a cap on it. If it is a small number, put a floor on it. Right? Does that make sense? So this is called gradient clipping. So we can do that. These are all regularization techniques, right? And then it can help you solve the vanishing gradient problem somehow. again, this one we already talked about it, batch normalization. So this is really useful. Everybody's familiar with the concept of normalization, right? So you know that what normalization is and what it does. So if I have a random variable z, then the normalized version of that is going to be, well, let's do x. The normalized version of that is going to be xi minus x bar divided by standard deviation, right? So this is a normalized version. What does it do? I don't know. If you have a distribution which is not necessarily normal, or we have some larger tails, something like that, then it can transform it to a more normal shape. So this is your normalization, right? And it doesn't need to be, the parent distribution can be any. It doesn't need to be normal. This can be anything. If I do this normalization, it makes it close to normal, right? And but for RNN, we use something called batch normalization. So this is different from simple normalization. Batch normalization means that look at the batch of data and then normalize it. Let's say you have a data set with 1,000 observations, right? And from that 1,000 observation, 80% is training, 20% is tests. So if you want to do classical machine learning in the cross-sectional data normalization, what do? You use those 800 observations, calculate the average, calculate the standard deviation, and then normalize the entire data with that, right? For time series, we don't do it that way. We use something called batch normalization. If I have the same 1,000 observations, but the model is processing the data in batches of observation, let's say 120, 12. So the normalization is going to be applied to that 120, to that 12, to that 24. So this is called batch normalization, and it should make sense. Okay. Yeah. And then another one, we can use different optimization algorithm. So for example, instead of a stochastic gradient descent, we can add this notion of momentum, just skip through those local optimals with, again, adding the momentum. One of them is add, and the other one is add RMS prop. So these are all the solutions that we can use for to solve the vanishing gradient problem. And the most important one is this. So this is the whole reason we do LSTM. Use gated cells, right? So we're going to use some sort of skip connections, which allows gradients to bypass some of the layers in a network and thus prevent them from becoming too small. So again, the idea is super simple. If you have done computer vision, you will see that we have something like this in ResNet architecture, residual network architecture. I don't know, imagine you have something like this. Oh, I'm just making up stuff. This is one hidden layer, another hidden layer, multiple hidden layers. We can connect these things like this. So this is another architecture called ResNet. And so we can make sure that it's as if there is a conveyor belt right across your network, that the data can jump on it, and then wherever you want, it can jump off, right? So this data is not going to be manipulated by multiple multiplication of gradients. So that's the idea of gated cells. And that's what we're going to cover in details now, right? So again, instead of using simple RNN, let's use more complex cells with gates which control the flow of information. So the key term is those gates are going to control the flow of information, and you're going to see mathematically how. Okay. So again, this is the analogy from the textbook, which I really like. It says that think of it as a conveyor belt running parallel to your sequence being processed. Information can jump on, transport to later time steps, and jump off when we need it. And how does this jumping on, jumping off happens automatically? Guys, this is all about training. Okay? This data is labeled. I know what is the output, right? I know what the model is predicting. I say, hey, this is the prediction, this is the output. Do your best, figure it out. Then realize that what information was relevant, keep it. What information was not relevant, forget it. Right? So this is what that gated cells are going to do, or those gates are going to do in general, right? So LSTM, long short-term memory. The short-term part is your RNN. Long-term part is the carry state, right? And GRU is a simplified version of LSTM. We're going to see in Python how we work with that. But again, the number of parameters is going to be smaller than LSTM. But LSTM is the most powerful one and most accurate one, but it requires a ton of compute power. So that's why sometimes we go with GRUs. Even with a simple data set that we have in the textbook with only 1,400 observations, and we're stacking a bunch of GRUs on top of each other, each epoch is taking 600, 700 seconds, which is crazy large, right? All right, so again, the point is that we want to keep track of information throughout many time steps, right? Let's see how it's done. So I want to open up this LSTM cell. So we're going to do it gradually. We start with the easy one, and then we get into the harder one, right? So let's start with the easy one here. Again, at the top, we have simple RNN, and we know that the input of simple RNN, let's use the same notation. The simple RNN is something is coming from previous state, and then something is coming from whatever time step we are here. These are the inputs and some information from before. And remember, I think Ryan asked a question. So this HT minus one is bringing every information from all the previous steps, right? So it's kind of summary of that. Which one is more important? We cannot quantify it, but the networks hopefully has a sense of that, right? And then there's going to be the output, right? So whatever it is. These are the actual ones. I want to write it output, so don't, because this is something that the model predicts. You can think of it as y hat t, right? So this is your simple RNN, right? And then we said we can unroll this simple RNN 24 times, 12 times, 120 times, right? Depending on what is that sequence length. Now we have this long-term memory. We're adding this long-term memory here. So what do we have? We say, okay, this is your input, and I want to decide what part of that input is irrelevant. Right? So guys, remember, the short-term memory, this is untouched. This is pretty much, I'm going to write RNN here. The short-term part is your RNN. You have seen this before, right? So LSTM must be at least as good as RNN, because it has that short-term part is exactly the same as RNN, right? So we are adding this long-term part. So this long-term part is CT, and then for that, I want to say, okay, if you are looking at the time series, I want you to pay attention to the, for example, data from the beginning, if it is relevant. If it is not relevant, forget it. If you have some natural language processing examples, it's a lot easier to follow these things. For example, you're saying a sentence, and then you want to see at the end of the day, that pronoun is going back to what at the beginning of the sentence, right? But the point is that we're going to say, okay, look at these gates. We're going to forget irrelevant information from previous state. So this is your gate number one. And we pass that thing to your carry state, right? To your long-term memory, right? So something is going to come from there, right? Forget and we're going to see how we do that. There are some gates, and those gates, we're using the sigmoid activation function. It's just a knob, right? That can turn it to 0 or 1. Forget everything, forget nothing, right? Again, how does the computer learn how to do that? This data is labeled. It's going to learn, right? So look at the error. If the error is large, it's going to try to minimize it. Go find the relative weights, change those weights, and find. So that's, I think, to me, the trickiest part was that, what do you mean forget irrelevant information? How the computer does it? Just remember, always remember this data set is labeled, and then you can look at the errors, and you want to minimize those errors. Then the second and third gates is input and update, right? So input relevant information. So we're going to input something relevant to, we want to introduce some candidate values. So these candidate values, we're going to show them with tilde, so C tilde. So this is the candidate for your memory, for long-term memory, right? And so those are going to be inputs, and you're going to update them selectively. So we'll see that what is that update cell does in the next slide. And then finally, output, right? So this output is going to be filtered version of your cell state. So the output is going to be a combination of your short-term memory. So the output has this HT-1 in it and CT-1. It's a combination of the two, right? And then it's going to output something for you, right? Oh, out of this cell, you can get your HT and you can get your CT. And this is your output. Again, output, your output is going to be your HT. In Python, when you look at the LSTM output, it's outputting your short-term. And what does it mean? It means that it doesn't take into account the CT. Yes, it will, but you will see it. If I show you the formulas, you will see that, okay, the CT is there, but what Python is outputting is this. If you specifically want to see what is the carry track, you have to change the code. But by default, this is what we mean. You know, the output is something like what happened in the previous state. Okay, so these two slides, we kind of talked about them, but I can still barely show them. Again, This is just me going over another example in the matrix form, right? I want to remind you how DNN work, how RNN work, and then now we go to the next slide to see LSTM. So let's say we had a univariate time series with 1,000 hours, and you're using 12 lags. Remember, this is DNN. For DNN, we use lags, a specific maybe created lags. So, okay, these are the 12 lags, 1 to 12, and it can be y to minus 12 all the way to y to minus 1. And then this is your first hidden layer, let's say with 32 nodes, second hidden layer with 16 nodes, and then one output. So this is your DNN, right? And then I wanted to, again, this slide is all about shapes, right? I want to talk about the shape of these matrices. So your input variable is going to be 12 by 1. So because we have 12 features, 12 lags. Your W1, look at that. These are W1s. We need to go from 12 nodes to 32 nodes. So that's why it's 12 by 32. Your B1, your bias stem for layer 1, I'm going to have 32 nodes. So it's going to be 32 by 1. Are we good? Okay. How did we do that? We say, okay, so I have W, I have B, I have X. This is a simple summation activation, right? Let's do simple summation activation. I have to do this summation activation, right? So I'm saying so basically W1 multiply X, because this is your econometric one, W1 X1 plus W2 X2 W2. So this is just simple linear function plus B1, right? And then if I want to write it like this, matrix algebra, W1 we say is 12 by 32, and then X was 12 by 1. So I cannot do that, right? So I cannot do this matrix multiplication. So that's why we need to transpose it. So that's why we have this transpose here. If I transpose it, then it's going to become 32 by 1. So 32 by 12. So 32 by 12, 12 by 1, so we get 32 by 1. And I need to add the 32 by 1, which is your bias term. So eventually, the output of the first layer is 32 by 1. Right. This is DNN. So the output of this layer is going to be 32 by 1. Are we good? Okay. So the output 1 is going to become the input for layer 2. So this is output 1, 32 by 1. This is going to become the input for your layer 2. So that's why I have it here. So then your layer 2 has its own weights. So what are the weights? We go from 32 to 16. So it's going to be 32 by 16. I need to transpose it, 16 by 32, multiply the output, which was 32 by 1. So here we get 16 by 1, and then plus the B term, we have 16 of these nodes, so 16 by 1. As you can see, the output of the layer 2 is going to be 16 by 1. Are we good? You see how these multiplications are done? And again, what are the parameters of the model? The parameters of these two, W's and B's. And then finally, we go from 16 to 1. So that's why we have, 16 to 1. I transpose it, so 1 to 16. And then output 2 is going to become the input for the last layer. So the output of this red is going to become the input for this purple. What was that? It was 16 by 1. And then I have one node at the end, so 1 by 1. So eventually, we're going to generate one by one number. Okay, are we good? So this is your DNN. Any question about DNN? Okay, let's do RNN. So I want to talk about this notion of length of the memory and depth of the memory. So this is really subtle. I want to pay attention to what is happening, what's going on. So we said that in RNN, you're not using features explicitly. You're processing the data in a sequence way, right? So let's say I have this simple RNN, and I have 16 of those cells, recurrent cells. So this means that this is going to unroll 12 times because my sequence length is 12. And I'm going to have 16 of them back to back. So here, we have 16 of them, 16 of these cells. So just imagine something like that. All right. Okay. Then I want to talk about this HFT. What is HFT? At the end of the day, this HFT, because I have 16 of these cells, it's going to be a 16 by 1 vector. So this is going to summarize the characteristic of your time series, right? And these are some numbers, right? So for example, and literally it can be any number. It can be 1, 0.2, 0.5, whatever. These are some numbers. But what does it mean? It means that, so let's say I started only one of these cells, right? Let's say your HFT is just one number, right? This is one characteristic of your time series. Is it trend? I don't know. Is it seasonality? We cannot label it, but it's something, right? So the idea is that the more of these recurrent cells I use, so I go from one of those features, you can think of them as features as well, right? To 2 to 3, all the way to 16 here. So I'm looking at more characters. Imagine I want to talk about you, right? And say you only have one feature. Say, okay, so boy or girl, that's gender. That's one feature. So if I give you more dimension, you know more about me. Okay, age, education, eye color, hair color. You see that? So we're looking at 16. So each of these cells, each of these recurrent cells is going to look at different characteristic of the time series. So that's why when we have, I call these things the memory depth. So this is the depth of the memory, right? So from different angles, you want to look at the characteristic of the time series. This sequence length, I want to call it memory length. So there are two numbers here, especially for time series. When you're doing RNN, it plays a very important role. So two numbers, the sequence length, that's going to be the length of your memory, and how many recurrent cells you're using, that's going to be the depth of your memory. Does it make sense? So again, these are the terms that I use. No, this is not scientific. Don't cite me. But if you want to cite me, just be cautious. This is the way that I understand it better. And so this means that even if your sequence length is 120, RNN cannot handle 120, but maybe LSTM can, right? Maybe transformer can. Even if the sequence length is large enough, but you don't have enough of these depth, then maybe your network is not going to learn it. You have to have a good combination of the two. Does that make sense? The depth of the memory and the length of the memory. All right, so that was one thing I wanted to talk about. And then now we can look at this age. Again, this is the output that I was talking about, right? So what do we have? We go from input to the hidden state, from hidden state to hidden state, and then finally, so this is what happens inside this recurrent cell, right? So going from input to, this is input to hidden state, right? So we have I showed with WHX, going from X to H, hidden state. And because I have 16 of these recurrent cells, it's going to be 16 by 1. And why 1? Because it's a univariate time series, right? If it was a multivariate time series, then I had more, because these are X0, X1, X2, but these are all 1. This is your airline passenger, 1 feature. Okay? I could have 14 of those features, just like what we did in the last theory lecture. But so that's why this is 1. And I transpose it, so it's going to become 16 by 1. Is this clear? 16 by 1. Why is it 16 by 1? Again, you can think of it, I have 1 feature, I'm connecting it to 16 of those hidden states, so 1 by 16. Now I transpose it, so it's 16 by 1. Okay. What is your X? Because there's only 1 feature, so it's 1 by 1. And then what is your hidden state to hidden state? Again, you need to go from time step 0 to 1 all the way to 12 here. This is the length of your memory, right? And this transition is pretty much the same as Markov process, but with some differences. Do you know what is Markov process? We call it memoryless kind of process. The idea is that what happens tomorrow only depends on today. So that's why we call it memoryless. I don't look into the previous time steps, right? This is pretty much like the transition matrix in Markov process. Just bear with me. Here, I'm saying from previous state to next state, from to. This is just like a transition matrix, right? And you see that because I have 16 of them, so this is going to be 16 by 16. From to, again, from the previous 16 to the next 16. So that's why this is a 16 by 16. And these are simply weights. The difference between this and a Markov process is that these weights are deterministic. These are literally constant numbers. Your network is going to update them, doing some optimization. Markov process, those are probabilistic. So that's the difference. But the notion is pretty much the same. We are transitioning from one state to another state, with these numbers. Okay. So that's why that's 16 by 16. So now you know this H 16 by 16, and then you multiply it by again, this is the entire RNN, that hidden state, everything is there, right? And in LSTM, you're adding CT to this HT. So that's why I wanted to start with HT and then say, hey, let's add the CT. So that HT, it used to be 16 characters, right? So that's why it's a 16 by 1. So this is the depth of the memory, right? 16 of them. So 16 by 16 multiply 16 by 1. So here 16 by 1. And then I have 16 of those recurrent cells. So that's why we have 16 of those bias terms. So if you do all these matrix multiplications, the output of this HT is going to be 16 by 1. Okay. So look at that. It says at each time step, give me the relevant information, xt, and what you bring from previous state, ht minus 1, and I'm going to update this sequentially. So that's the, and I can confidently call this the short-term memory, which is forming in RNN. And so again, the takeaways from this slide is that, remember, there are two important numbers here when you're doing RNN in Python or LSTM in Python. You have to pass the sequence length. When you hear the term sequence length, think about the length of your memory. And it's not enough to have a lengthy memory. You need more, you need more depth to your memory as well, right? So that's we call it the number of recurrent cells. So these are the units that you're going to add to the network, and this is the sequence length that you're going to add to the network when you're doing Python. Okay? All right. So this was so as you can see, the output of this one is 16 by 1, right? I can stack another RNN on top of that. And so this was RNN number 1, and I can stack another. If I want to do just one RNN, I say, you know what? Give me all the time steps, whatever it is, in this case 12, and then 16 of those. So this is the shape, right? However, this is number of observation and shape. If I want to stack another RNN on top of that, you're going to see it in Python video that when I stack a bunch of RNNs on top of each other, basically something like this, stack another one with 32. So again, I'm making it the depth of the memory even bigger, which adding more layers. If you want to add this second network to the first one on top of the first one, your second one is requiring input length as well. The input length is the same. Sequence length is 12, right? If I pass this thing to RNN2, your Python is going to complain. It's going to say that, hey, I need it, because the sequence length is 12, I needed 12 inputs. You're giving me one input. Does that make sense? So that's why there's this switch in Python to say return sequence is equal to true or false. So if you want to stack a bunch of layers on top of each other, the layers before, you need to make sure that the return sequence is true. So that you're going to output everything. So if it's going to make it many to many for previous layers, right? So it's going to output everything at every single step. So it's going to add another dimension to your output. Your output is not going to be 16 by 1. It's going to be it's not going to be non-16. It's going to be non-12 16. Does that make sense? So then I can pass it to the second recurrent neural network. This is just pretty much the same as what we saw here. So now here I have 32 nodes. Does that make sense? Because in the Python video, when you see me that, and I'll do the code and I'll do one without return sequence is equal to false, once with false, once with true, and you'll see what is the difference. What happens to the weights, what happens to the output. The idea is that if I switch that off, it's going to make it many to 1. If I turn it on, it's going to make it many to many. And if your layer is in between or in the first layer, you want to stack something on top of that, you have to make sure that those outputs are on, are true. Okay. Now, with that background, I think hopefully you have a good understanding of HT. Now let's see, or HT minus 1, let's see what is this CT minus 1 and where is it coming from, right? Again, I'm going to break down this cell into 4 steps and I'll walk you through it. And remember, guys, this HT was super simple, right? We said, again, in RNN, we had something like this. The output was summation, activation, right? So WX, XT minus 1 plus WU, what do you call it? WU and WHH. Yeah, these are all HT minus 1 plus B. we're going to see the exact same thing, but repeated 4 times because we have 4 of these gates, right? So that was, you can think of an RNN as a single gate cell and LSTM as a 4-gate cell, right? And the 4 gates are the one that we're going to see why we need either of them. Again, I want you to focus on this part, the carry state, the long-term memory. The short-term is pretty much the same. Okay, let's start with phase 1 or gate 1. So again, this is what each of those gates are going to do. The first one, we call it forget gate, right? There's a formula, and all of them are the same. Look at that. This await multiply something, and then plus hidden state multiply some weights, and then some bias term. So this is pretty much the same. So I have activation, and activation is a function of both previous input and this is previous hidden state and input, and then some bias term, right? So this is good. You will see something like this for all the gates. Just pay attention. See, so you will see something like that for all of them, right? Let's see what are each of those gates doing. So the first one is forget gate, right? So we're going to forget irrelevant information. So it says use previous cell output and input, right? So this is, we're going to use the previous cell output, which is ht minus 1, and the new input, which is xt, right? So output, this is your ht minus 1. Are we good? Okay. Then we're going to add this sigmoid activation function to that. So far, this is pretty straightforward. So I'm going to add a sigma on top of that and say it's going to filter the values between 0 and 1. So if that output is 0, it means that nothing from this previous hidden time steps and this input was relevant for long-term memory. Just do not pass any information there. So, and again, you know that sigmoid is between 0 and 1. So if I pass this thing and it turns out to be here, it's not going to pass anything to the next level. Are you following? So value 0 and 1, completely forget versus completely keep. So if that thing, again, how does the network know it is 0, it is 1? This is labeled data. We're going to look at the errors. Optimization is going to take care of the weights. Okay. I think let me give you a quick detour. Do you remember lasso regression from machine learning course? Ridge, lasso, elastic net. So do you remember that this was, again, this is a detour, and I think it's relevant. So imagine you have a data set, cross-sectional data set like this, beta 0, let's use machine learning language, b plus w1 x1 plus w2 x2 plus w3 x1 to the power of 2 plus w. Actually, let me make it simple, just one feature because I want to visualize it. x1, let's just call all of them x, right? w1x, w2x to the power of 2, w3x to the power of 3, w4x to the power of 4, and etc., right? And let's stop there, keep it simple. So imagine this is your functional form, and the data is this. This is the data. As simple as that, right? If I use lasso, what will happen to W2, W3, W4? They will become 0, right? Again, if I use lasso, remember this is a regularized or penalized regression. Lasso is going to say your W2 is equal to W3 is equal to W4 is equal to 0. How did the lasso did that? Look at the loss function, look at the errors, minimize those or mean-squared errors, whatever, and automatically decided to set these W's as zeros. Do you see what's going on? We're doing exact same thing. When I say that this sigmoid is going to determine if it's something relevant for the future or not, it's doing exactly something like that. If it is not relevant, automatically it's going to set those weights to 0. So are you good about the forget gate? So again, we want to pass something relevant to the long term, right? To this carrier state. All right, let's go. So these are the ones that we are forgetting. What are we inputting to that, right? So that's the input state, input gates and update gate. So we have, let me see if there's anything else. So far we cleared only this one. I'll talk about every single thing, these things that you're seeing here, but so far we cleared the first one. Then we have this I and C tilde, right? So again, all of them look at that. Look at I, C tilde, F. They're all function of previous hidden state and X. Look at that. Previous hidden state, X. Previous hidden state, X. Right? But you're all getting the same data. All getting the same data. Again, we're going to do, and each of them have their own set of weights, right? So this one has its own set of weights, WF and BF, WI, BI, WC, BC, and etc. Right? Okay. So then I'm going to do another sigmoid here. So the sigmoid layer is going to decide what values to update. And the tanh layer, so here's another activation function. Why tanh? Why sigmoid? Again, this is the architecture that they designed, right? So the sigmoid is more straightforward. You want to put it between 0 and 1. The tanh, you want to say that, you know what? These are the candidate values. I don't want to force it between 0 and 1. Let's do -1 and 1. It's symmetric. If I want to pick one activation function, I will pick tanh instead of sigmoid. Obviously, I'm not going to use ReLU or leaky ReLU, right? Because you don't want to filter these inputs right away to get the candidate values, right? So the tanh layer is going to generate new vector of candidate values. So this is going to be your CTLN. So these are going to be the candidates for your long-term memory. They're not necessarily long-term memory. We need to manipulate it. They're just candidates, right? And those candidates are coming from your inputs in previous hidden states. Is this clear? You start from somewhere, and we use tanh. We call them, those are candidates. Let's pass it to my carry state and see what we can do with that. Okay. All right. Then, so tanh generate new vectors of candidate values that could be added to the stage. So are we good in here? So we have, again, we're going to look at the combination of the two in the next slide, right? So whenever you see this cross sign, we're multiplying them elements by element. Let me write it somewhere. So elements-wise multiplication. So these ones are elements-wise multiplications. And this is simple summation. This is simple sum. Yeah, let's look at the update cell. So we need to remember, guys, we said, let's come up with some candidates and let's add some inputs to update those candidates. Now we have to multiply them elements-wise, right? So again, it's all about how we figure out what is in this carry state. So if there is multiplication, if this is elements-wise, so I'm going to say ft multiply ct minus 1. So this is elements-wise. And then it multiply c tilde, again, this is elements-wise, right? So the idea is that we're going to apply forget operation to the previous internal cell states. Remember, we have some number here. We're in the, let's say you're in the middle of something. If you're at the very beginning, very first step, t times step 0, that ct minus 1 is a random number. Okay? That's random number generated. Then from step 1, those numbers are updated, so we have something, right? So we're going to say multiply this thing elements-wise to your forget gate. Go back to this. If those things are 0, so it's gonna become irrelevant, right? Are you following? And then this is where you're gonna update your candidate values, right? So add new candidate values is scaled by how much we decided to update, right? So again, these are going to be, if you're me, your biggest question is that how? Always remember it's supervised, looking at errors. It's learning those things, right? So we covered this forget gates, input gates, update, and then we know what are these multiplications, and we added them, right? So this is the adding part. So this is where your long-term memory is forming, right? So your long-term memory is a combination of the previous long-term memory multiply something which is not relevant anymore or which is relevant, multiply some updates. Where are those updates coming from? Directly from the value of the input at that time step and what is coming from short-term memory. Are we good? High level? Yep.
So would it be correct to say that first part, ft times ct minus 1, that essentially is creating a vector that in certain places has zeros because of the forget function, and in the second part of that, the it times c tilde or c tilde t, that has values corresponding to the places where the zeros have been input in the first part, and you're adding them together to basically build again.
Exactly. So if you have 16 of these recurrent cells, what is the dimension of CT? 16 by what? Literally, what is the dimension of this FT? So it's going to be 16 by, so again, literally, this is elements-wise multiplication. So this is going to be your F, this is going to be your CT minus 1. If some of them are zeros, it's going to just update your CT minus 1, make them 0. Exactly. The same story for I and CT late.
But the opposite ones are going to be zeros because it's basically filling the values that were zeros.
Yeah, if imagine this is, I don't know, 2.5. So the multiplication of these two is going to be 0. Again, this is elements-wise. The mathematical notation is this. Elements-wise multiplication. A circle, and a dot and a circle around it. So if you see something like this, that's a notation for element-wise multiplication. That's why you can multiply 16 by 1 and 16 by 1, because you cannot matrix multiply Z2. At least the dimension doesn't. All right. Yeah, remember, if I had 16 of these cells, at the end of the day, the shape of HT minus HT was 16 by 1, and the shape of this one is 16 by 1. So just be aware of the shapes, right? You're updating a vector throughout the network. Okay. All right. So the last one, this is your output one, right? So look at the output. This is where I told you that the output is a combination, is what is coming from short-term memory and long-term memory, right? So your output, we have OT here. This is what is this? Please make my day. Just look at that. I have XT, HT minus 1, and a sigmoid. What is this? This is your RNN. Literally your RNN. Are we good? Okay. So I have that one. This is definitely exactly what comes from RNN. And I'm updating that output of the short-term kind of memory with long-term memory. Okay. That's why we're saying that this OT, which is the RNN part, short-term memory, multiplied, again, 10H, why 10H? We try different activation functions. They want to make it symmetric, so 10H is symmetric, so that's why they use it. Definitely, we don't do ReLU or because you don't want to filter your memory, your long-term memory, especially if it has negative numbers. If I have negative numbers, if I do ReLU or liquid ReLU, it's going to cut that memory. So you either want to do sigmoid or 10H. So which one is symmetric? 10H. So that's why we're doing it. Right? Okay. So 10H. Again, this is a filter. Again, this is the nonlinear version of your long-term memory. Does that make sense? Again, summation, activation or nonlinear version of your long-term memory. Why we add nonlinearity? Because it captures more complex pattern. And then you're multiplying it by this thing, this short-term memory. This is going to be your output. Okay. So sigmoid layer decide what parts of states to output. So we talked about this. The 10H layer squash values between -1 and 1. We know that. This one output filtered version of cell state, right? So this is it. This is what we're going to get out of. So when you do LSTM, Python layers dot LSTM, whatever, blah, blah, blah. So you're building your networks. At the end of the day, this is the output. This is what by default Python is going to output. So just be aware. Okay, that's it. We did it pretty much it. So how do you feel? Again, high level architecture of LSTM. Just be aware there's short term, there's long term, and how these gates are roughly working. Forget something, introduce some candidate value for the long term, and then update that candidate value with the forget thing. Keep track of the relevant long-term information. At the end of the day, update your short-term memory with the long-term by just doing this multiplication. So this is how LSTM is working. The thing is that I think François Chollet make a very good paragraph about that. Do not try to say, hey, this part of the output is because of the forget gate, or this is because of the can update gate, or this is because of the output gate. All these weights are updated simultaneously. There's no sequential things happen. They all happen at the same time.
Yeah, that's what was confusing it's like
you cannot say exactly. Again, this is word by word from Francois Chalet. We cannot say what part of this output is generated because of the forget gate. It doesn't work like that. Everything is happening together. Yeah, that was a great observation. Okay, now with this, you will see why the backpropagation is less painful. Guys, why did we do this? Simply because to avoid the keep track of the long term and avoid the vanishing gradient problem, right? And so LSTM uses gates to regulate the information flow. Now we know exactly what we mean by regulating information. This new cell can better capture long-term dependency. Again, up to 100 time steps. Even more than that, it's again, LSTM doesn't work. This fights the vanishing gradient problem because now when you're doing backpropagation, and if you're going through the long-term memory, this part, the path that you go back is not like the RNN. So it's when I'm taking derivative with respect to this long-term memory, it's bunch of elements-wise multiplications and summations. So this is different from RNN that we had that. Still, there's something like this, but this is for the replaces S with H's, but I'm taking derivative with respect to C now. So H is there, but we're looking at the C as well. So what for C, these gradients are going to be less touched compared to gradients in the short-term part of the memory, right? Something like that. Yeah. So this is the Python part. Again, to remind you guys, it's really simple. So you have a sequence length. This is I want you to look at it as the length of your memory was 120. And this is your 14 features. This has nothing to do with your memory necessarily. This is the depth of your memory. Okay, so let me write it down. This is length of memory, and this is depth of memory. And again, this is completely made up terms that I use, but I think it works. I like this analogy, depth of memory. Look at that. It used to be simple RNN, now it's LSTM. That simple. Yeah, we added a dense layer at the end. Let's do this one and then call it a day. So let's start with RNN. I have 16 of them, right? So 16 of these cells. And remember, my input has 14 shapes, so it's a 14 by 1. Is everybody following? 14 by 1. This is my input feature. You good? Okay. I'm passing it to a recurrent cell. How many of those hidden states do I have? 16. So the weights of X to H, what is the dimension? Help me out here. 14 by 16, 14 features to 16 recurrent cells. We good so far? Then from these things to themselves, from this hidden state to hidden states, what is the dimension of that one? Can anybody help me with that? So what is the weight for H to H? You have 16 of them. Think of RNN, not LSTM yet. Think of RNN. Does that make sense? You go from 16 of those cells to 16. Guys, do you remember this transition matrix? This one? From to. Okay, I have 16 of these cells. I'm using the same numbers. Okay, so that's why it's a 16 by 16. Are we good? How many bias terms do we have? If this is 16 of those cells, 16. Okay, the bias is getting 16. All right, so let's add them. So 14 by 16 plus 16 by 16 plus 16. Does this make sense for RNN? Okay, for LSTM, how many of these set of weights do we have? 4. One for this, one for this, one for this, one for this. You see that? So I need to multiply it by 4. Use your calculator, you're going to get 1984. You're good? All right, so again, this is from Francois Chalet's textbook. I just wanted to show you what are those weights, right? So these are WHH, we have 4 of them. These are WXH, we have 4 of them. And we have 4 bias terms. that's why we need to multiply. Whatever you saw in RNN, I want you to just, as practice, go home, replace this LSTM with simple RNN, and then you will see this number is going to get divided by 4. So that's how the parameters are calculated in LSTM. All right. So what is the output? The output is 2.53 in terms of mean absolute error in the test set, which is outputting your base test, your benchmark. And it also beat your naive forecaster, we know. But there's a slight problem here. You're overfitting. How do I know that you're overfitting? Because look at your validation MAE right away. It's kind of around 2.5 and it stays there. So how do we fix that? Can we do better? The answer is yes. Improving the simple LSTM, how can we do that? There are different ways. The first one is, guys, if you have something like this, overfitting in deep neural network, what do? You regularize your network. Okay. So what is one way to regularize the network is dropout. For time series or recurrent neural networks, we call it recurrent dropout. So this is different from your dropout that you know. So the dropout that you know is something like this. And you randomly switch these cells on and off, randomly. Okay. For recurrent cells, you don't want to. So there are two types of dropout. This one, you know, for recurrent layers, you don't want to do it randomly. You just want you want to make sure that randomization is the same for all the time steps. So for example, if you're switching step 1, if you're turning step 1 and step 5 off, you need to make sure that in all the recurrent ones, step 1 and 5 is off. Otherwise, you're shuffling time series. Does that make sense? So this is what the recurrent dropout is doing. I think I had a sentence or, well, let's see. So again, this is one way. Another one, make your model more complex. So instead of one LSTM, just stack a bunch of them. You can do, your network can be a combination of RNN, LSTM, another LSTM, another GRU on top of that. You can go crazy with that, right? And you can do different dropouts, right? You can do recurrent dropouts, and then after that you can do simple dropout, recurrent dropout. You can do batch normalization. You can go crazy with your network here. So this is answering, can we do better? Okay. So the first one, the dropout, is the regularization thing. It's fighting the overfitting. This is say that, okay, you want to do a combination of the two, right? So you want to regularize, but at the same time, you want to make the model more complex. To just, again, try to find different aspects of the data, right? So this making model more complex does not fight the overfitting. If anything, it's going to help the overfitting. The other way. And another one is using bidirectional RNN. So processing the same information differently. So time series chronologically, anti-chronologically. This is mostly useful for NLP, and we'll see that for time series it doesn't work. So let's look at them in Python. So what is a recurrent dropout? Again, the same dropout pattern. So that's the difference between regular dropout and recurrent dropout. So how do we add it? LSTM, recurrent dropout, 25%. Let's see the one with dropout, is it doing better? Yes, it's doing a lot better. And right now, we have this problem of validation loss is less than train loss. How did we fix this? We said, okay, let's make it more complex because these dropout is overkilling it, right? So let's make it more complex. We make it more complex, and yeah, at some point, the train performance is better than validation, and we get something like that, right? So how did we do that? We added a bunch of GRU layers. The GRU is a simpler version of LSTM. It has fewer gates, so it has fewer parameters, but it's faster than LSTM. It's something between RNN and LSTM. Okay. We are stacking a bunch of those GRUs, and this is what I was talking about at the beginning of the class. You see that return sequence must be equal to true if you have these RNNs in the middle. Because this thing is expecting whatever it is, it's 120, a shape of 120. So if you don't pass 120 output from the first layer, it's going to complain. You following? Okay. Yeah. So with the complex regularized, so it's both at the same time complex and regularized. Complex coming from the fact that you're stacking a bunch of them, regularized coming from the fact that you're adding dropouts. This complex regularized network is giving us the best performance, 2.39. And each epoch is taking 600 seconds. This is length. If you do just for 10 epochs is 51 hour. So that you see what's the limitation. Bidirectional LSTM, again, for text, it makes sense, A, B, C, D, E, and all. If I think of this sentiment analysis, right? If I give you a bunch of words, it really doesn't matter if I go from the beginning to the end or to the end to the beginning. You get the sentiment, positive or negative. So it works. So for natural language processing, bidirectional LSTM works. But for time series, no. If I look at the stock price in reverse, what did I get? Nothing. Nothing. If you get something, it's a sign that market is random walk. It's another sign that market is random walk. All right. So yeah, for temperature example, the bidirectional LSTM is strong, but underperforms. I think the numbers that I updated was 2.7 something. Again, in the slides on GitHub, the updated numbers are there. So this slide is slightly different. And you'll see that that's going to be actually the worst performer, 2.7 something, the bidirectional one. Yeah, that's it. So let me wrap up the course with these final messages. As you can see, deep learning is more an art than science, too many moving parts. I think you can agree to that, right? There are too many moving parts. Number of units, these are the cells we're using in recurrent layers. Number of stack layers, amounts of dropouts or recurrent dropouts, number of dense layers, sequence horizon, optimizers, learning rate, et cetera, et cetera, et cetera. So it's to this part is that you literally have to try and error. But there is one rule of thumb, though. The bigger, deeper the network, the better it performs. So we are capped by compute power. So if you have unlimited compute power, unlimited resources, you can make the most giant network and it's going to perform better.
All right, back to the studio. I hope you enjoyed this almost an hour long theory lecture of LSTM, and let me know what you think. And we should be able to wrap up the session now. So just one last reminder, these deep sequence modelings in general should be applied to datasets that the past is a good predictor of the future. And as you can see, this is kind of completely against what we see in the stock market. So when it comes to stock market prediction, I don't want you to use LSTM and apply it to price and use univariate time series forecasting and think that it can do any better than an A forecaster. It might be able to outperform an A forecaster, but depending on what is the time horizon, if you backtest these things, the trading strategies that ride on top of these models in the long term, it's gonna have hard time outbidding even your A forecaster. Does it mean that you cannot use deep learning for stock price prediction? That's a different story. It's not in this setup, right? Not in this setup that you have a univariate or even multivariate that you want to forecast into. You can use deep learning to create some very well studied and engineered features, and then use those features and indicators to add to your model to come up with a better predictive power, not applying LSTM or RNN directly to the price. So yeah, I think in the future I'm putting together a course for deep quantitative trading, namely algo trading, and I'll talk about all these nuances, right? So this course is going to be prereq for the other one, so you should know how to, in general, forecast a time series. And after that, how you should go from time series forecasting to creating trading strategies, because these are completely different ideas. All right, so this is it. That was our module 7. And we have only 2 more Python lecture videos that I go over univariate time series forecasting using RNN LSTM and multivariate time series forecasting using RNN LSTM. Until the next one, take care. If you're looking to stay updated with the latest versions of the course's materials, please make sure to follow my GitHub and remember to refresh your repositories periodically. If you find yourself needing a bit more background in econometrics, machine learning, or deep learning, check out my other YouTube videos for additional insights. And for all the latest news and quick updates, don't forget to follow me on Twitter. Thanks for joining me, and let's keep learning together.